Hello, everyone, and welcome. Today, I'm going to talk to you about learning representations of web pages. I hope that after this talk, you will not only walk away with more awareness of the immense potential of this underexplored area of deep learning research, but also with knowledge of the tools you need to get past the entry barrier and start doing something about it. My name is Stefan Magureanu. I'm part of the web automation research team at Klarna, and today I'll be presenting some of our more recent work. Before joining Klarna in 2018, I completed a PhD in reinforcement learning at KTH. Since then, I've been working on different aspects of building autonomous agents for the web throughout my 3-year tenure at Klarna within various teams. Today's talk is going to be structured in 2 main sections. I'll start with an introduction to the field and where it lies in the landscape of deep learning research, as well as what opportunities lies ahead and why we should be solving this problem. The second part of the talk is going to be focused around how to do something about it. Here we'll discuss a bit about the state of the field now, and I'll introduce you to the tools you need to get started and have an impact. Okay, in order to set the scene for the rest of the talk, I'd like us to look at the internet through our machine learning goggles, and probably the best place to start are autonomous agents. In general, an enormous amount of research is being poured into developing agents that can autonomously complete tasks for us in our physical world. Self-driving cars are a great example of this, but also delivery drones, robot warehouse workers, vacuum cleaners, lawnmowers, and so on. The promise is that these autonomous agents will free our attention and time from tedious tasks like parking and fetching our car, long commutes and shopping trips, mowing lawns, vacuuming, and so forth, and leave more time in our day for the fun stuff, the stuff we really want to be doing. In comparison, almost nothing is being developed to help with tasks that need to be completed over the internet, and usually through an internet browser. We're spending more time than ever on the internet, and e-commerce alone is a multi-trillion euro industry, to which we dedicate around 3 hours of our time every month as users. Yet no work seems to be going towards a self-driving internet browser to free our attention from working through the same tedious steps, like completing checkout flows, navigating to and configuring products, looking up information and what to do next, or just sitting through page load times. It feels like it would make a lot of sense to automate all of these inconveniences. So is it really worth it? Let's just look at the checkout process on an e-commerce website as an example application. A study by the Baymard Institute this year found that 80% of users who abandoned the purchase online in the 3 months leading up to the study did so because they found the checkout process too complicated. 24% of users quit at least once because they were asked to create an account. A self-driving browser could navigate all these inconveniences for us. Inconveniences that we perceive as so severe that they cause us to stop, turn around, and repeat this process somewhere else. Only this one use case can save 20% of the users at least one purchase attempt per quarter. That's billions of dollars that are currently being fumbled around every quarter. There are lots of similar workflows that we now just mechanically execute and spend time on without giving it much thought. We actually spend a lot of time just scrolling and looking for information on websites and stuff to do next, closing pop-ups, be it on an e-commerce web store or even on your organization's internal web applications. Ideally, we shouldn't have to do any of this. All this work has the potential to be automated and can free our precious attention and time for just the fun stuff on the internet. Going back to autonomous agents, a self-driving browser would, in theory, have to complete roughly the same high-level steps as a car would. As an example, it needs to figure out where it is in its environment and what the consequences of its immediate actions are. Am I on a checkout page? If I click this button, will I complete the checkout or will I empty the cart? And what it needs to execute in order to reach a desired result. It needs to navigate to a product, configure it, add it to cart, go to the checkout, fill in some forms, and click finish. The longer term strategy it needs to execute in order to solve a more complicated task. It's just the environment that these agents operate in that's really different. It's no longer a physical world, it's our internet browser. At Klarna, we're working on such features. Our shopping assistant works in very similar ways to the scenario I've described earlier. The assistant knows how to complete a checkout flow. Users just need to confirm each individual step. It is, however, only enabled on a set of popular merchants, less than 500 out of the 20-odd million e-commerce websites that are around these days. And it requires analysts to label the actions required on each merchant. To put this in self-driving car of equivalent terms, the car could only park themselves in a few specific parking lots. Maybe your apartment, maybe the mall, and maybe a few e-cabs around the corner with a known layout of their parking lot where cars can take the same fixed route every time to get to their spot. It's a great start, but in order to scale this up so that it works everywhere, such that you can confidently just take your hands off the wheel or mouse or phone in our case, and let the agent finish any task for you, we need deep learning. We need algorithms that are able to look at the website and figure out where it is and what it needs to do next. And this leads us to the topic of learning representations of web pages. Like I mentioned earlier, in order for an agent to figure out where it is and what it's doing, it needs to take a website together with its interactable elements and distill it into an algorithm-readable representation. One vector of numbers that describes the state, and one more for each action available. Similar vectors should correspond to similar actions in terms of desired effect, and the same should hold true for the vectors representing states. And they should also be much lower dimensional than the original output. In our case, the DOM tree, which is huge, has a lot of variance in it. So we need to boil this down into a lower dimensional representation that algorithms can work with. So we want it to be algorithm readable. Once you have these powerful algorithm readable representations, you can train policies on top of them such that they would be able to learn the high-level steps that need executing in order to solve the task. In reality, once we have this first step, you can really do any kind of prediction or classification, not only predicting which form needs filling next, for instance, but any information retrieval task as well, like extracting product details from a product page. The first step, however, remains this one, to compute these representations. So we've talked a bit about the area and what the value of solving this problem is. And let's say I've convinced you. Awesome. Now, let's do something about it. If you were to start working on this topic today, where would you be starting from? Like I said earlier, deep learning over the web is very much a green field of underexploited potential. This holds particularly true when it comes to research in this area. There are only a few, maybe 2 or 3 papers that appear every year on this topic, most from the same group at Google. In order to get started, there are 2 major hurdles that you need to overcome. The first is we need realistic data sets. And by realistic, I mean we need data sets that are complex enough to be able to represent examples we are likely to run into in the real life, and diverse enough such that the random real-life examples will not differ too much from the examples in our data set, which means that algorithms that train on your data set would exhibit performance that would generalize well in the real world. Secondly, we need these efficient learning algorithms to train on these realistic data sets, neural network architectures in our case. So, well, what do we have to start with? What are the best existing data sets and algorithms for this problem? Let's start by looking at the state-of-the-art data sets. There is an acute absence of realistic data sets, which slows down the development of research in this field. The most advanced evaluations in the state-of-the-art, and on which the most recent publications in the field rely, use the following two sources of data: the Structured Web Data Extraction, or SWDE dataset from 2011, and the World of Bits environment from 2017. The SWDE dataset is a collection of around 124,000 web pages, each with a few labeled elements. It covers around 8 classification tasks, but only contained pages that were crawled from about 10 websites per task. This makes it very easy for models to overfit the template, particularly as the DOM trees are very similar. Like I mentioned earlier, there is only about 80 templates algorithms can learn. This limits the challenge of learning the structure of a generic web page and does not satisfy our diversity requirement. The mini world of bits environment can randomly generate almost an infinite combination of web interfaces. It covers around 100 tasks, but these pages are nowhere near realistic. They only contain a handful of interactable elements each, and hence they're nowhere near close to being useful in practice. It therefore doesn't satisfy our need for realistic complexity. So the Klarna product page dataset. The data sources present in research publications so far are still insufficient for realistic evaluation of the methods currently being developed. And this is one of the main hurdles when it comes to getting started in the field. When we got started, however, we were able to source our own dataset in a way that addresses some of these issues. And after we validated that this dataset is indeed fit for more realistic use, we'd like to make it public under a non-commercial license in order to enable researchers to better understand how well their algorithms perform. So today we're going to be making public this Klarna product page dataset. And this dataset has around 50,000 individual product pages from 8,000 distinct merchants, from 8 different markets. We have a bunch of languages represented, most significantly English, German, Swedish, and Finnish, but several other languages are present as well. It's therefore substantially more diverse than the SWDE dataset. The median size of DOM trees in this dataset is around 2,000 elements. These are snapshots of real-world pages, so are therefore complex enough to reflect real-world performance, therefore satisfying our complexity requirement as well. You can download the dataset in 2 possible formats, as web traversal library snapshots or MHTMLs. The WTL snapshots can easily be loaded using the web traversal library. This is a Python library that we developed here at Klarna over the past 3 years, and it's also released as an open source library. You can find the link to it at the bottom of the slide. The other format you can find the data is MHTMLs. This is the closest we have to lossless snapshots of web pages. It provides something similar to an HTML document, but which has embedded in it all the media required to render the page, modulo some JavaScript snippets, which unfortunately get lost in the process. The MHTML dataset requires substantially more space, measuring around 50 gigabytes for the entire dataset. So let's look at what a single data point in this dataset looks like. In our case, what does a product page look like, and what labels we can find? Looking at this example page, the pages themselves generally contain 5 labels for each product page, chosen in such a way so as to offer a good balance between diversity of prediction tasks and real-world use case scenarios. The tasks covered here are classification of action elements. In our case, we have the buy and the go to cart button, and information retrieval, where we look at extracting the image of the product, the name, the price, and in our experiments, we also try to extract something called the subject node. This is the lowest common ancestor of all the ever labels. And semantically speaking, it's the node in the DOM tree most likely to contain all the important information on this page. Each of these tasks rely on a different amount of contextual information to correctly predict the required element. The buy button, for instance, is usually quite self-contained and does not require algorithms to interpret what's around it too much, to a large extent. For the subject node, however, the story is quite the opposite. For detecting the subject node, algorithms need to look around the page in order to identify what makes the subject node the subject node. In this case, it contains very little information in and of itself. And the classifiers would therefore need to inspect what is around it and within it in order to realize the semantic role of this element, the container of all important information on this page. Similarly, for the name and price, we need to distinguish between the names and prices of recommended products versus the main products, and so on. We'll now talk about algorithms and which approaches to factoring in contextual information on web pages performs best in our experiments. Okay, so we've talked about what datasets you might want to look at when getting started in applying machine learning to the internet. Now, let's see what algorithms exist for this task and how well the state-of-the-art performs on our more realistic dataset. Like I mentioned earlier, we're looking at algorithms capable of identifying relevant contextual information spread out around the web page's DOM tree. So we look in our experiments to the most popular three approaches from the literature. The first category of algorithms are sequence-based neural networks. The second are convolution-based neural networks. And the third are DOM-specialized neural networks. I'm not going to go into much detail about what these are, but they are highly specialized architectures that are specifically targeting DOM trees. You might notice that one of the methods that first comes to mind is missing from this list. You might ask, why not just use computer vision? It works for classifying complex figures like cats and faces. Why not apply it here? The main issue with applying computer vision approaches lies in, well, they're mostly practical in nature. For one reason, it's hard to match the borders detected by the algorithm to the elements underneath. This is because usually the elements are have a white color and a white background and have no distinguishable border that the algorithm can select. Secondly, when used in real life, you have issues with occlusion, like pop-ups and additional layers and stuff. In theory, the DOM tree should contain all the information you need to render the image of the page. So it should contain all the same information that the screenshot should contain, but at a fraction of the dimensionality. This is the main reason why we only looked at the neural network architectures that target the DOM tree, and why previous work also only looks at DOM trees for this particular task. Coming back to our three main contenders, the sequence-based models are variations of long short-term memory networks capable of handling trees. And the way these work is they scour DOM trees one node after the other, propagating what information it deems relevant towards the node we're trying to make a prediction on. The effect being that the information from far away tends to weigh less relative to contextual information from nodes that are closer. The second group of algorithms are the convolution-based models. These also aggregate information from around the node, that we're looking to classify, but it does so for a sample of a node's neighborhood, and all at once rather than sequentially, meaning that information from a node that's further away is not really weighed down if it's considered. However, it is less likely to be considered because it's the sampling procedures usually offer lower probability as you go as you move away from the node of interest. And finally, the DOM specialized networks. You can find their descriptions in the references at the end of the slide deck. And I'm not going to go into how they work because they're very complex and very specialized for this particular task of processing DOM trees. So now that I've introduced the three main contenders, let's look at how well they did. I'm not going to dwell on this slide. I'm going to leave it here for you to examine later. And for now, in the interest of time, let's just focus on the best performing algorithms. In our experiments, we trained these algorithms to produce a score for every element belonging to each of the labels present in our dataset, covering both action elements and information retrieval tasks that I mentioned earlier. The algorithms then report the element with the highest score for each class, and we check whether this element matches the labeled ground truth. In this graph, you can see on the y-axis the accuracy of each algorithm's prediction. And on the x-axis, you have each of a task. We can see that the most promising candidate in our case is the GraphSage graph convolution network, despite this model not making use of any of the text available on the website. The second contender was the Freedom Web Specialized Architecture. In this graph, we also present the fully connected network, which is just a two-layer dense network that takes no context into account and simply uses the local features present on each node. The first thing we notice is that the achieved accuracies don't look that great. We have most of them capping at somewhere around 80% accuracy. This is because the problem of pointing out one element of the thousands comprising a web page that match one label is much harder than just showing an element to our classifier and having it guess what kind of node it is. This is because whenever you just have to extract one element out of thousands, there are many opportunities for there to be a statistical outlier that would confuse your classifier. Therefore, your classifier needs to be particularly robust to negative examples. The second thing we might notice is that when identifying the buy button on the fifth set of columns here, none of the architectures make good use of any of the context on this page. They do just as well as the fully connected baseline, which doesn't even attempt to factor in any context. The story changes for the subject node and the main image, where the convolutional neural network is able to gain a substantial boost from using the context around the node to estimate their class. It's almost twice as good as the following contenders. Overall, the graph convolution neural networks tend to outperform the ever baselines. So it's probably a good place to start if you were to try your hand at this problem tomorrow. So we've mentioned earlier that there are two main hurdles to getting started in this field of web representation learning. The first is the lack of realistic data sets, and the second is the unknown efficiency of algorithms in the literature. In this talk, I've introduced you to a new realistic data set that we're making public today. You can find links to download it in the very last slide of this deck. And we've also explored the efficiency of some of the most popular neural network architectures to provide you with the best starting spot currently available. I hope that after this talk, you feel more confident getting started on your journey to apply machine learning over the web. And would like to wish you all a fantastic rest of the summit. And I think now I'm ready to answer some questions. So let's see in the Q&A section if there's anything. I don't see anything here, but I will join the discussion on the page in a few seconds. And yeah, goodbye, everyone, and have a nice rest of the summit.